Thank you. Ah, yes, at the magic dial. Excellent. The GL transitions and OpenOffice. Excellent. So I'm going to talk very, very quickly, as you see, about I/O and profiling it. And perspective is key. Let's take Richard here, who's a very clever guy. He's got a brain that's maybe 20 centimeters away the information is. Maybe if you want to find something else out, you go and find a book on your desk 80 centimeters away. Maybe you have to walk across the room to find something on a shelf to look something up. But when we start to get a bit further away, maybe in the Middle East, what's equivalent to this distance in computing terms, right? Well, we have our registers in our CPU, and the numbers, of course, vary, but these are ballparks, maybe half nanosecond, level 1 cache 2 nanoseconds, memory 10 nanoseconds. Well, it turns out we have to go to the Middle East to try and get data off the hard disk. The disk seek time is about 8 million nanoseconds, like that, 8 milliseconds, right? And it doesn't change to go and scrape the data off. So it really pays to avoid seeks, where you have to go and fiddle around on the disk and try and get the data out of it. So OpenOffice, yeah, OpenOffice cold start is still not what it could be after a long time of me working on it, and it's getting better, I promise you, particularly the easy to measure part. But as you see, as we go, lots of the time here is really just I/O time. You can measure that very easily. You run it warm and you run it cold, and yeah, you just see this. And OpenOffice does a whole load of stupid things. That's very true. You can run strace on it, and you can see all these system calls it's doing that it shouldn't do, and so on. But they all fit in the small part here. They're not I/O specific. They are clearly in the 20% and decreasing piece. The 80% is clearly the I/O time. And my thesis is that Linux should let you do stupid things faster, right? Because people go doing stupid things all over the place. The next problem is that on the Linux kernel, at least, it's very difficult to get deterministic runs of your I/O time. So you really want to measure this thing so that you can shrink it bit by bit. But the problem is you can't really measure it. It just doesn't work. Even if you cold boot across cold boots to the same point, you don't get repeatable timings. You can also try all these other nice things. There's things that help here, dropping VM caches, ioctls. But plus or minus 10% is a reasonable jitter that you would see. And of course, if your win is only 5%, which is a worthwhile win, it's just lost in the noise. And why? No idea. The kernel is really broken in this regard. And there's nothing complicated happening. This is not an elevator type thing. There's just one I/O request happening after another. And yeah, the kernel people say things like this: just rebuild your kernel with this patch set, which is deeply unhelpful. And the kernel also has tweakables, so you can set different things, and it'll, apparently speed up I/O. Yeah, but that's not very helpful either. So iogrind then hopefully tries to address this problem by providing a cunning solution. So what we do is we run our application inside Valgrind here. I have a pointer, I believe. Excellent. I can, yeah, here. And that generates a nice trace file. Actually, it's just the standard out dump from Valgrind, or this Valgrind skin. And then we have a little GUI. Now, simultaneously, we grab your disk and we dump your file system, so we have a layout of your file system, and then we can simulate them all together inside here with a disk simulator. And this gives us pretty pictures. We apply our brain, and shortly, hopefully, we can then improve our software. Of course, the problem is this tool is really very beta, which is why I'm showing it to you. It shows some interesting things, but of course, yes, you could go very badly wrong with it. Ooh, nice. Don't lean forwards, just a tip. So here is, oh dear, oh dear. I'm too loud, I think. That's probably the problem. It's congenital there, unfortunately. So here is a lot of the stack. Ah, that's better. Hey, good. If I shout, I don't get feedback. So cool. So here is a view of the entire aggregate stack time. This area is simulated time. So the axes are meaningless, but the area is meaningful. It's much like kcachegrind. And what we can see is that this guy here, called check icon, is taking a whole lot of time. So we can dive down into that. Well, we could go up a bit and see the immediate stack frame there. And you see on the left here, there's a whole lot of stack frames. And this is interesting because there was a bug in SUSE Linux Beta 2 of 10.3, in which it was doing a whole load of icon theme validation stuff, which was doing a load of I/O it didn't need to do. So that's pretty easy to find that. You can break it down by files. So you can see what type of file is consuming the most time, where it is on the file system. You can look by address. So this is looking at virtual memory pages and when they're first touched. So this is starting to show you the working set of your application. And you can see all sorts of interesting things. So for example, as you map libraries, let me explain the axes first, so maybe it's a bit more meaningful. This is virtual memory address down here, compressed. So there are huge holes in virtual memory. We throw them away, and we just draw compressed VM there. This is simulated I/O time on the other axis. So you see as you map your libraries and you come down, you start doing lots and lots of I/O, reading bits of them, and then there's sort of nice bits of backwards I/O. Lord knows what's going on there. And hopefully, as time progresses, you start to actually execute code, and you can see some of the stack frames there from where these pages are being touched. But you see that really locality of reference is a bit of a myth inside this kind of thing. The interesting thing is the icon cache I was showing you earlier is here, and you can clearly see that these people are touching every single page in this rather large memory map for apparently no reason, which is not necessary. So hopefully you can see silly things as they happen. Now there's another tool here. I hope I used the right file system model to show it to you. And this allows you to browse your filing system. So on the far right here, we have your entire file system. I guess the white bits aren't used, the black bits are. And here we can also see it. If we scroll down, we can start to see some of the things in the file system. There's a particularly interesting cache file here, I hope, if I've got the right version, which maybe I haven't. Well, anyway, you can see fragmentation in some of these files. So, for example, this 555 CFS here, you can see a split across many pieces. And I try and use the tone of these things. So let's hope that is the same file. The intensity of the color is used to delineate order. So the file is ordered. Hopefully, a perfectly defragmented file will go from dark to light, just as a continuous thing. And so when you start seeing different blocks of color in the middle, that's bad news. And some of the files, particularly SQL-like databases, get horribly fragmented during use. Finally, there's a third thing, which is called Scribble, which is much like the file system view, but it lets you see multiple I/O. So as I select different I/O transactions as they happen in order here, you can see that it's starting to draw Scribble on the page. And this is starting up gedit, which is just a fairly simple text editor. And as you see, as we start to select it all, it ends up with really quite a lot of I/O happening here. Lots of seeking about, all over the place. And of course, if you read all this data linearly, you can read it really very quickly. But if you start doing this sort of stuff, clearly your I/O performance goes way, 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 way down. So you don't want to do that. You want to read it nice and linearly. Hopefully you also see that there are sort of hot zones here. Clearly there's something interesting down here to gedit. I don't know what it is. We can perhaps select it and see what it's doing. Okay, so it's doing a whole lot of GStreamer stuff, apparently, loading various things. God knows what's in that. Oh, no, I lied. It's ATK. It's accessibility infrastructure. And when that package was installed, it was installed at a different place to, some other library it was using. And they're all scattered all over the disk. And the net result is your system is slow if you haven't started an application recently. So it sounds hopeless, and the situation is pretty bad, I would argue. But I'd like to show you how you can actually use the tool to improve your application, not just get depressed about it. So one of the big performance problems in OpenOffice we solved between 1.1 and 2.0 was startup time performance was incredibly dire. And we found out much of this was in the linking stage. So as you linked, it would touch lots of pages which would be forced in, and they were all scattered all over the place. This was very slow. So we wrote a very clever application that would page all of these files in and touch each of their pages one by one by one by one. And then it would all be there, if you had enough memory, and then it would start up a lot quicker. And this was a major noticeable user performance improvement. However, we have this little application here that goes around touching libraries. So first of all, it touches all of the star writer library, and then it moves on to SVX, and then it moves on to something and something else. And as it goes, you see the pattern is building up. And hopefully, if we zoom out a bit, you can see maybe a bit more of it. It's doing some nice linear reads of each library, but between them, it's still dotting all over the place. So with a very simple sorting scheme, using the information you can get from the directory, which is the inode number, so without actually having to stat the files, we can get a hint as to what order the files were laid down in, hopefully. So the inode number is approximately good as an ordering hint. And hopefully if we come here and we zoom out, and I scroll down a bit, because now we're starting at the top instead of the bottom, hopefully you can see that we're starting to read fairly linearly here. So some bits we don't read, but at least we mostly don't dot about. So you can then prove that you you save a certain amount of time, and guess what? Each time you run it, you save exactly the same amount of time. 100% deterministic, and you can point other people to it and say, look, I saved this amount, and they can't argue with him because they can't reproduce it. So, you know, the iogrind never lies because there's nothing to contradict it, which is great. So that's fun. But having done all these things, you then come up with a whole load of other crazy ideas. So, for example, it would be really nice to install whole systems and see how file system layout is affected by this, to tweak the kernel layout algorithms and reinstall in a few seconds. Of course, not using real data, just using bogus data, and see what happens. Just rerun the entire I/O pattern of an install, and then rerun all of the applications, from Oracle databases through random desktop startups, through booting the kernel, and say, ha, everything got faster, or 99% of apps got faster and 1% got really slow and they were broken anyway, this kind of thing. So to do that, we really need to be using SystemTap. Running an entire install through Valgrind, I think, would be not feasible, much as I love Valgrind, and it is really cool. Incidentally, writing a plugin for it is relatively easy. I encourage you to do that. And then just using a cut-down kernel to simulate it so that we can actually try the things in line. And various other interesting things that come out. Out of my 4 GB OpenSUSE install, I have 16 megabytes that describes all of the file system layouts, all of the names, where they are on disk, and where their inodes are. If I compress that, it goes down to 2.6 megabytes, which is 0.065% of the file system, easy to fit in memory. And the problem with directories is it's basically pointer chasing. You can't tell where the next, the third directory level down is until you've gone, statted that thing, read it, and then found, oh, well, it's just before where I was reading. So there's this information problem that is only solved by seeking if your directories are laid out like they are at the moment. So I think there are lots of things that need to be done to improve file system allocation information, and our file systems are not really good enough at the moment without Band-Aids. Problem is, you talk to the server guys about this, and they say, oh, but we could have 1 billion files in a directory. You're like, that's true. My laptop doesn't have, 1 million files total. It does, has relatively few. So there's, again, a server desktop imbalance here, and someone needs to take this task on from a desktop perspective. So if anyone has time, see me afterwards. Why should you ever read a directory or read an inode ever again? You should just read 2.5 megabytes in a fraction of a second when you boot the machine and know where everything is. So yeah, there are various hacks you can do to improve layout as you install packages, which are quite fun, such as, for example, installing the whole package set into a single directory, hard linking it to where it's supposed to go, and deleting the original. And you can control the layout in these rather hackish, but perhaps quite effective ways. Various other things, that's Alan Cox's idea, not mine. I can't claim credit for it. Open size, for example, saying how large you want the file to be as you open it, so that you don't get fragmentation caused by multiple people opening files and appending to them slowly. Late block allocation, as some file systems do. It's foolish to allocate the data blocks for your file as you open it, or as you append to it. You should only do it idly as you actually write to the disk, because you can delay and reorder much better then, and hopefully the file's closed and you know how big it is. Yeah, and here's the crazy idea. Why not serialize your whole inode and directory cache across mounts? So as you unmount your file system, you just shove all of that information in a nice linear block and rehydrate it, and hey, save a lot of seeks as you bootstrap. So I think that's my crazy ideas. Here's where the code is. The only deterministic solution, yeah, get those 5% wins. If you have 10 5% wins, that's pretty good. But if you didn't have any one of them because you couldn't measure it in the noise, that's pretty sad. Particularly because many of these optimizations can slightly confuse the code flow, and make things more complicated, yet hard to argue for, but really, really important. So yeah, iogrind's useful for applications, file system authors, lots of potential for expansion if you want to play with it and have a hack. It's easy to hack, it's written in C#, it's really simple. And yeah, there's the URLs. Thanks to AMD for funding it, Julian Stewart for producing Valgrind, Federico Mena for doing pretty graphical things, and my Indian friend Sanka for helping out with it. So thank you. Very good.